This is part 12 of the series Circles, and in this part we're going to look at the segments of secants and tangents theorem. In the last part we looked at the segments of secants, and now we're going to be adding in a tangent segment. The segments of secants and tangents theorem says if a tangent segment intersects a secant segment at a common point outside the circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So it's similar to the segments of secants theorem in that we have one secant segment here, so the entire secant segment times its external piece is equal to the square of the tangent segment. So rather than having two pieces to this tangent segment, we only have one piece that takes the entire side. So again, dB, the entire secant segment, times its external piece, CB, its external segment, equals the square of the tangent segment. So it's a little bit simpler. Proof, on the other hand, is about the same, maybe a little bit more complex. But let's go ahead and take a look at that proof and see how different it actually is. In this theorem, what we have is we drew in two auxiliary segments, one from AD and one AC. And the idea there is to create two similar triangles here, triangle BAD and triangle ACB. And you can see that angle 2 is intercepting arc AC. So angle 2 is 1/2 the measure of that arc, and that is by the tangent chord intersect theorem. And we can see that angle 3 is also intercepting that arc. So angle 3 is 1/2 AC. So you can see that angle 2 and angle 3 are going to be the same measure for different reasons, but they're going to be equal. Angle 1 is being shared by both of those triangles. So we can see that we have two angles of one congruent to two angles of a second, so those two triangles must be similar. That's the root of our proof. Based on that similarity, we're going to go ahead and write a proportion, and by algebraically manipulating that proportion, we should be able to get this form. So let's go ahead and start out by saying originally that angle 2 is 1/2 AC and angle 3 is 1/2 AC. We have angle 2, measure of angle 2 equals 1/2 the measure of AC, and that is the tangent chord intersect theorem. And then the measure of angle 3 equals 1/2 the measure of AC, the inscribed angle theorem. Now, because these two angles have the same measure, we can say that those two angles are equal to each other, and therefore they are congruent by the definition of congruent angles. So just to streamline this a little bit, we said the measure of angle 2 is equal to the measure of angle 3. That's the transitive property of equality. If A equals B and B equals C, then A equals C. And then because the measure of the two angles are equal, the two angles must be congruent by the definition of congruent angles. Now we have angle 2 is congruent to angle 3. We can say that angle 1 is congruent to itself by the reflexive property. And therefore, those two triangles are congruent by angle-angle similarity. I have now angle 1 is congruent to itself by the reflexive property of angle congruence. And that gives us triangle BAC is similar to triangle BDA by angle-angle similarity. This leads us to our proportion. And because the two triangles are similar, all corresponding sides are proportional. Therefore, I can come up with a proportion that's going to give us this relationship. So let's generate a proportion. First, we'll get ourselves some space at the bottom here. We'll generate a proportion and see if we can't manipulate that into this form. The proportion I generated was CB, the first and last letters of this triangle, correspond to AB here, as go back to this first one. AB corresponds to DB. So that's our proportion. Now if we multiply both sides by DB, on the left we get CB times DB, which is what we needed. And if we multiply both sides by AB, we get AB squared on the right hand side. So by multiplying both sides by DB and AB, we will eliminate this fraction and uncover our final statement. And there we have it. So that proves that the entire secant segment times its external segment equals the square of the tangent segment. Let's go ahead and use these last two theorems that we proved, that is the segments of secants theorem and the segments of secants and tangents theorem, and work with a few examples. This example is going to be one of the segments of secants theorem, and so we have two secants intersecting at a common point. We know that the entire secant segment times its external segment equals the entire secant segment times its external segment. We're charged with finding x, so let's begin. We know that the entire secant segment is x plus 3, and we're going to multiply that by its external piece, which is 3. And that's going to equal the entire secant segment, which is 5 plus 6. And we're going to multiply that by its external segment, 6. So multiplying these together, we get 3x plus 9 equals 66. Subtracting 9, we get 3x equals 57. Divide by 3, x equals 19. And so there we have it. Okay, let's work another example. This is another example of the segments of secants. And so let's begin. We know that the entire secant segment times its external piece equals the entire secant segment times its external segment. So to start off with, we know that x plus 6 times x equals 5 plus 4 is 9 times 4. Working from the left, x times x is x squared, x times 6 is 6x, and that equals 36. You can see that we have a quadratic equation here, so we're going to solve this, set it equal to 0 first, and then solve for x. So x squared plus 6x minus 36 equals 0. It doesn't appear that this is going to factor cleanly, so I'm not going to waste a lot of energy on any other sophisticated methods. Let's just jump straight to the quadratic formula and find out what the roots are. So the quadratic formula, in case you don't remember, is negative b plus or minus, that's x, equals negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is the coefficient of the squared term, b is the coefficient of the linear term, and c is the constant term. So we have negative 6 plus or minus the square root of b squared, 6 squared is 36, minus 4 times a times c, all over 2a. Alright, let's figure out what this is. That's 36 plus 36 times 4. That gives us negative 6 plus or minus the square root of 180 all over 2. Now if we simplify this guy, we have the square root of 180, that's 2 and 90, 2 and 45, 2 does not go into 45. 3 goes into 45 15 times. 3 goes into 15 5 times. And there are our prime factors. So you have one pair of 2's, one pair of 3's. So that's 2 times 3, square roots of 5, 6 square roots of 5. So this is negative 6 plus or minus 6 square roots of 5 all over 2. We can factor out a 2 here, so that gives us negative 3 plus or minus 3 square roots of 5. Now, since we're looking for a value of x, which is a segment length, we really don't care about the negative value. That's all we're concerned about is the positive root. So negative 3 plus 3 square roots of 5 is the value of x. If we want to approximate that, we can put that in our calculator, and we get approximately 3.71. So there's our value of x. Let's look at one more example before we go. Here, we're looking at an example of the segments of secants and tangents. We have a tangent segment here and a secant segment. So the theorem states that the entire secant segment times its external piece equals the square of the tangent segment. So starting this off, we know that x plus 8 times its external piece, 8, equals 12 squared. So 8x plus 8 times 8 is 64 equals 144. 144 minus 64 is 80, so 8x equals 80, and x equals 10. So that was a fairly straightforward example, but the important thing to understand is that the entire secant segment times its external segment equals the square of the tangent segment. And that wraps up the segments in circles. Now for the next part, we're going to look at equations of circles. So rather than split that into two separate videos, I'm going to push that out to the next part, and we'll look at equations of circles in part 13. I'll talk to you then.